Good evening. I would like to, in my role as the director of the Berkeley Center for Theoretical Physics, I would like to welcome you here for this wonderful public lecture by Fabiola Gianotti, one of the heroes of modern experimental particle physics, and also, oops, did I press something wrong? One of the superstars of popular culture these days. But I'm not here to introduce Fabiola. I'll leave that to our colleague, Marjorie Shapiro. I'm here to frame the bigger picture of why this event is happening. It's not here just because we are so excited that particle physics has entered the era of discovery. That is indeed very exciting. It's a collective effort which requires both experimentalists and theorists to contribute significant efforts on all sides of the understanding of the fundamental laws of the universe, which is our main focus of the research here. This event is not isolated because it's a part of a bigger conference, a 3-year celebration of our esteemed colleague and dear friend, Bruno Zumino, who is turning 90. He actually turned 90 last week. And he is one of those theorists who really created a huge impact on the field of high-energy theoretical physics as well as mathematics. He's extremely humble, so he only gets a small picture in that small corner of this transparency. But his humble nature is more than matched by the amazing impact he has had on the lives of many theorists and experimentalists. It's not really a stretch to say that big machines like the one in the picture are built precisely because of his imagination, and we are so happy and privileged to have celebrated his 90th birthday here over the past 3 days with people flying all over the world, the leading theoretical and experimental high-energy physicists, all eager to celebrate his profound humanity and his amazing contributions to science. Bruno, unfortunately, is not here with us due to his fragile health, but we are very happy to wish him a speedy recovery and a happy 90th birthday. So I think it's time to cut to the chase, and I'm happy to introduce my colleague, Marjorie Shapiro, who is a professor in the physics department as well as a senior scientist at Lawrence Berkeley lab. She's been involved in the ATLAS experiment since its very beginning, and she's going to introduce Fabiola.
So I'm really delighted to have the opportunity to introduce Fabiola Gianotti to all of you. Fabiola has been a friend and a colleague since 1994, when a number of us at UC Berkeley and Lawrence Berkeley Lab decided to join the ATLAS experiment at CERN. At that point, ATLAS was still in the conceptual phase, but Fabiola was also already taking an important role in it. Fabiola's whole professional history has been devoted to trying to understand the fundamental interactions of nature and to look for the new parts of nature that we haven't seen before. She did her PhD thesis on the UA2 experiment, searching for supersymmetry, which is perfectly appropriate for this meeting since Bruno was one of the people who invented supersymmetry, and so this really brings us around to the purpose of us all being here. And then after that, she joined ATLAS at the point where it was still just a concept. On ATLAS, her first contributions were in the area of electromagnetic calorimetry. You'll see in her talk that the electromagnetic calorimeter that was finally built was absolutely essential for the discovery of the Higgs because it's a good photon identification and resolution that made the Higgs discovery possible. At the same time she worked on ATLAS, she also joined the Aleph experiment at the E+E- LEP collider and continued to try and find SUSY. And I should say right now, while we still haven't discovered supersymmetric particles, we haven't stopped looking. And I hope in a few years, all of you will be here and will be able to make an announcement of something truly new. At the moment, there's no evidence for that, but with the energy going up, we still are hoping for the best. So On ATLAS, Fabiola's played a number of roles. She was physics coordinator, then deputy spokesperson, and she just finished her second term as spokesperson of ATLAS. And ATLAS is like the US presidency in the sense that collaboration only allows people to be spokesperson for 2 terms, and she finished those 2 terms. And I think if we didn't have term limits, she very easily would have been elected for a 3rd, although I'm sure she's happy to be able to have the chance to do physics with her own hands again. ATLAS is a huge collaboration. It has 3,000 collaborators on it, and so you can imagine what must be involved in keeping something on the rails that's that large. Fabiola was our spokesperson during the full period of our data taking, 3 years where we collected all of the data she'll be talking about. And during that period, we published a total of 250 papers. And I can say that she had something to say about every one of them. She read all the papers, she commented on it, and one of the highlights of her term as the head of the collaboration was really making sure that the quality of the science was kept high, but at the same time, we were able to release results in a timely way to the rest of the world. And that really was a challenge, and she stood up to it and did a great job on it. The only other thing I wanted to highlight about Fabiola is she's always felt it was very important that ATLAS have a mission for education, and she's taken the role of the undergraduate, the graduate, and the postdoctoral students and postdocs on the experiment very seriously. And she's always made sure that they got the credit they deserved for the work they did in the trenches, and they also got the learning experience that they should have. So I think it's fitting to have her talk at a university as well as being involved in a national lab, because she's always taken that educational mission seriously. So with that, I'll stop, and we'll get on to our main event, which is Fabiola's talk on the Higgs boson in our life.
Good evening. I would like to thank Marjorie Shapiro for the very nice words. She and the Berkeley group in general have contributed immensely to the results that I will show now. So I'm very pleased to be here and to have the chance to share with you the excitement for this very special discovery, which represent a crucial step forward in our understanding of fundamental physics and the structure and the evolution of the universe. And I'm particularly happy to do so at the occasion of Bruno Fest, as Peter mentioned before, because Bruno has been one of the people who have mostly inspired us experimentalists to build this Large Hadron Collider and to undertake this very challenging adventure, and he has played a very important role, as we will see later on. As you know, the Higgs boson has been discovered at CERN last year. At the Large Hadron Collider, the most important, the biggest accelerator ever built by mankind. So I would like to go step by step, and I will spend a few seconds to tell you what's CERN. So CERN is the largest particle physics laboratory in the world. It's located in Geneva, Switzerland. It's a place, a very special place, where over the last 50 years, scientists from all over the world have been doing fundamental research, awarded in many cases by important discoveries and Nobel Prizes. It's a place where the scientific goals require the development of high-tech technologies in a large number of fields, technologies that then are transferred to society. So the most famous example is the World Wide Web, which was introduced at CERN by Tim Berners-Lee in order to facilitate the exchange of information among the scientists involved in CERN experiments, and then it has changed the way society accesses information. And actually, on 30th of April, it was the 20th anniversary of the web. So happy birthday to both Bruno and the web. CERN is also a place where we train young people, tomorrow's scientists, but also school students and their teachers through large number of initiatives, and is a fantastic place to bring nations together, pulling nations together by attracting scientists, about 10,000 scientists from more than 60 countries from all over the world. So I have one slide on CERN history. CERN was founded at the beginning of the 50s with a twofold goal of restoring European research after World War II by creating a center of excellence, and at the same time mitigating the tensions, the symptoms of the Cold War. Today, CERN is a global enterprise. It brings together 20 member states. All of them are from Europe, but also many non-member states, and also nations which have a particular state as observers, as the United States. The yearly budget amounts to $1 billion, and it is contributed, is shared among the member states in a way proportional to their income. $1 billion means, on average, 1 cappuccino per European citizen. On average, I stress on average, because it depends on the latitude. In Italy, the cappuccino is very good and very cheap. And then you move north, and it becomes very expensive and, okay. Fine. So this budget is used to pay the salary of the staff, the CERN employees, and in large part to develop the infrastructure, like the accelerators and various infrastructure that are used by the worldwide community to do experiments at CERN. And this worldwide community, as I mentioned before, comes from more than 60 countries, so member states here in blue, non-member states in red, and observers in green. And you can actually see that the US contributes the single largest contingents with 1,700 scientists. So US physicists contribute a lot to the LHC, but also benefit a lot from their participation in these activities. So beyond this social consideration, which perhaps I will also touch upon again at the end, CERN's primary mission is science. So what we do is we study the elementary particles, among which the building blocks of matters, the electrons and the quarks, and the forces that control their behavior at the most fundamental level. So we all know today that matter is made of atoms, and atoms are made of a central nucleus surrounded by clouds of electrons. The nuclei are made of protons and neutrons are made of even smaller constituents called quarks, the quarks. As far as we know today, quarks and electrons are elementary particles. That is, we cannot cut them into smaller pieces, and they are the fundamental constituents of matter. So everything in this room is made of electrons and quarks. So you, me, this high-tech electronic gadget, etc. So they are the fundamental constituent of the universe. However, only, we'll come back to this later on, 5% of the universe, because the rest we don't really know how it is made. So particle physics at modern accelerators allow us today to study the fundamental laws of lecture at the level of the quarks. So we are able to study the fundamental matter at the level of a scale, down to scales of 10 to the minus 18 meters, so 1 billionth of a billionth of a meter. So you can imagine, you can associate this, describe this accelerator as very powerful microscopes that allow us to scrutinize matters at this level. At the same time, these studies allow us to get some insight about the structure and evolution of the universe. So the very small allow us also to understand the very big. And the reason is that we know today, based on cosmological arguments, but also a huge number of observations, that the universe originated from a big explosion called the Big Bang. And at the beginning, it was very hot, and it was essentially a gas of free particles. And then with time, it expanded and cooled down, and then the particles started to stick together to form atoms, and then light elements. And then with time, the macrostructure that we know today, like planets, galaxies, stars, etc. But at the beginning, beginning, at the very beginning, it was a gas of particles, and so by studying the behavior of elementary particles and their interaction at very high energy, we can try to reproduce the phenomena which have characterized the early universe. So how do we achieve this in practice? So we do the following things. And from now on, I'm going to give you a description which is scientifically not rigorous. So I do hope that it remains in this room among us. I see a camera there, so I'm a bit worried. But anyway, so what we do is to accelerate two beams of particles, for instance, two beams of protons, as we do at the LHC, and to make them collide. So you can imagine that in this smash, this collision at very high energy, you can imagine, although it's not really true, that the protons break up in 1,000 pieces, like when you collide two Ferraris at a very high speed. They go in many pieces. So in this way, we can understand how the constituents of the protons, the quarks, and the other particles which glue them together in the nuclei, the so-called gluons, interact. So how fundamental matters behave. At the same time, in the energy, from the energy released in the collision, new particles can appear, can be created, because we all know Einstein equation E equal mc squared, so we know that energy can be transformed into matters, and vice versa. And the higher the accelerator energy, the heavier the particle that can be produced in the collision. So particles that have not been observed until now at previous accelerators, perhaps because too heavy, may be observed and produced today at the most powerful accelerators that we have today. Then this particle decay into lighter known particles like electrons, photons, which are very well known in our day-by-day life. And so what we do, we surround the collision point with instruments called particle detectors. These are high-tech instruments made of different layers of different material. Can be silicon, can be argon, can be gas, can be scintillator, etc. And we try to, with the goal of reconstructing all the products of this collision. So the particles that have been produced in the collisions, and so this allows us to, in some sense, to have a full picture of the collision events, and then we can move to the interpretation phase and understand what happened in the collision itself. So we need three things. Well, actually, we need four things. The first thing that we need are human beings and brains, okay, scientists and brains. But then, apart from that, we need accelerators, we need particle detectors, and we need computers. So accelerators are usually underground rings. As you can see here, this is an image of the Large Hadron Collider. You can see the underground tunnel. You can perceive curvature of the LHC, and this object, these blue tubes here, are very powerful superconducting magnets. So the accelerators are made essentially of two elements. They are made of an electric field, which are used to accelerate the particles incrementally at each turn. So every turn you give them a kick, and then you accelerate them. And very, very, very strong magnetic fields, which are needed to guide the beams in the ring and to keep them inside the ring itself and to bring them into collisions. Detectors, as I mentioned before, are massive instruments with which we surround the collision point, and we cover essentially the full solid angle around the collision point, and they allow us to detect and to reconstruct the trajectory of ideally all the individual particles produced in the collision, to measure their energy, to identify them, understand if this particle is an electron, a photon, a muon, or another particle. And at the end, we have a full picture of the collision event. And finally, we need a lot of computing resources to store, distribute, and analyze the vast amount of data produced in the collision. Now, the most complex and advanced high-tech accelerator detectors and computers of the history of particle physics have been conceived and realized and built in the framework of the Large Hadron Collider, which is actually one of the most ambitious projects in science, more in general, and has required the the efforts of the international community, strong effort of international community over more than 20 years. We had to introduce innovative concepts and technologies in a huge number of fields, from cryogenics to material science, electronics, data treatment, etc. So DLHC is a 27-kilometer accelerator ring located near Geneva, across the French and Swiss border. So this is a view of the region. Here you can see Geneva Airport. Here we have the main buildings, the main site of the CERN laboratory. These little white dots indicate the border between Switzerland here and France there. I live here, but you don't care, I guess. Okay, so this circle, unless you want to come for dinner, I'm a very good cook. So. Then you need to know where I live. So this circle here indicates the location of the LHC ring, 27 kilometers. Of course, you don't see it in the surface. It is 100 meters underground. So over the last 3 years, as Marjorie has mentioned, we have been circulating 2 proton beams in the 2 opposite directions, accelerating them and making them collide in 4 points. The energy of the collision, ATV, I will explain perhaps later what it means, but anyway, let's look in relative proportion. It's 4 times larger than the energy achieved so far at previous accelerator. And the previous most powerful accelerator was the Hadron Collider at Fermilab. So this machine, this accelerator, reaches energies that are a factor of 4 higher, thanks to very high-tech superconducting magnets. So this beam has been made collide at 4 points of the ring, where the 4 stars are yellow stars are located. And at these 4 points, we have built very big underground cavern in which we have installed very massive and big detectors, which have the following name, ATLAS and CMS. These are the 2 experiments which have observed the Higgs boson and reported, announced the discovery of this new particle. And then LHCb and ALICE, which are somewhat smaller and dedicated to some specific goals. I will not mention them. Now, US laboratories and universities have contributed in a very important way, in a very crucial way, to the 4 experiment and to the accelerator, and in particular, what's going on? Yes, a team from Berkeley University and Lawrence Berkeley National Lab has been active in ATLAS since 1994 and has contributed in a very, very crucial way to the construction of the detector and to the analysis of the data and to the results. I will come back to this point later on. So ATLAS is one of the 4 big detectors. Actually, is the biggest one. So note the size of this object. It is 45 meters long and 25 meters high. So this is to be compared the size of 2 human beings, a man and a woman, because we promote equal opportunity in the experiment. So the 2 beams collide here in the center, and then surrounding the beam pipes, you have several cylindrical layers made of different materials, and then the detector is closed in the forward and backward region by 2 end caps in order to close the full, surround the full and cover the full solid angle around the collision point. So why so big? Because the particles produced in the collision are extremely energetic, so you need big volumes to absorb them and to measure them with high precision. At the same time, we want to measure the trajectories of the individual particles produced in the collision, and at each crossing between the 2 beams, thousands of particles are produced in the collision, and we want to measure the individual trajectory of the individual particles with micrometric precision. 1 micron is 1 millionth of a meter. So we need very granular detector with many individual sensitive elements, and actually we have something like 100 million individual sensitive elements which produce individual signals, which we use to track this particle. And to give you an example, this is a collision event in the other experiment, CMS. Actually, not all the particles produced in the collisions are shown here, but the 2 beams have collided, and you can see by eye the individual signal hits that, for instance, this particle has left in the sensitive element of the detector. Here you can see some energy deposited in the calorimeters, which are part of this detector, etc. So you can almost by eye, in this particular event, which is quite clean, you can almost by eye reconstruct the trajectory of the individual particles, and therefore have a picture of the event. So in some sense, these detectors can be imagined, can be described as giant digital camera, which take picture. However, they have to be ultra fast, because the two beams of protons interact, collide inside each experiment 40 million times a second. So you have to take 40 million pictures a second. We do not store all of the picture, only a few hundred are really stored and then analyzed, because otherwise it will be essentially impossible. But the detector has to be ready to, in some sense, to take this, to look at the data with such a speed. It was also a very challenging engineering effort, because of course you have to install such massive detector, so big and so heavy, in an underground cavern. So I would like to show you some picture. This is the ATLAS underground cavern as it looked in June 2003, when the excavation work finished, and the cavern was handed over to us, to the experiments, to ATLAS, and so we had to start to install our detector. So we started with the feet of the support structure, and then we lowered one by one the various elements. In particular, this big object that you can see here, these are coils, these are magnets, superconducting magnets, 100 tons each, 25 meter long, so very high-tech object. And you can see that in October 2005, a large part of the detector was in place. And again, you can see the comparison with a human being. So quite impressive. Also impressive and remarkable is the size and geographical distribution of the collaboration of physicists participating in the ATLAS experiment, and of course CMS is similar. So in ATLAS we have 3,000 scientists coming from 38 countries from all over the world. So the yellow, this map shows in yellow the countries participating in ATLAS. So you can see many from Europe, South Africa, South America, Australia, China, the US, etc. So it's really a worldwide effort. And the US is contributing to ATLAS through about 40 universities and laboratories for a total of 600 scientists. And note, please, more than 250 students. So you will see also in the following, for instance here, that typically students are at the level of account for about 30% of the collaboration. So these collaborations are actually quite young. So I mentioned that Lawrence Berkeley National Lab and the University of Berkeley University team is working in ATLAS. They have a very strong group, 60 scientists and many students, 20 students between undergrad and graduate students. And they've made very strong contribution to the detector construction. In particular, they had a leading role in the construction of the so-called pixel detector. This actually, I mentioned that we have 100 million of sensitive elements. Actually, 80 millions of these 100, most of them are in the pixel detector, which is the detector closest to the beam line. The first layer is at 5 centimeters from the beam, and it's made of this 80 million of pixel sensor with pitch 50 micron. And this detector is very powerful in reconstructing the huge track multiplicity which comes out of the collision very close to the beam line. Of course, when you move out from away from the beam line, the density of tracks decreases, so you don't need such a high-tech and high granularity detector. But the Berkeley group also has made a very strong contribution to software and computing, and now to the physics exploitation of the data, and in particular the Higgs discovery. So I like to show this plot, which presents the age distribution of the ATLAS population in blue for boys and in red for girls. And you can see, well, as I mentioned before, we have more than 1,000 PhD students, so not to count the young postdocs. So more than 1/3 of the collaboration is young, and these young people are really very energetic, and they are the driving force of the experiment with their competence and with their energy. You can also see that most of the actually in general of the scientists are below 40 or so. I'm here in this bin. Don't laugh, it's not very. But you can also see that the fraction of women is at the level of, on average, of 20%, but this fraction increases in the young generation. So there are more and more women in the young generation who undertake an activity in fundamental research, which is, of course, very good. Okay, I will skip the computing, not to bother you too much, and now go to a few additional numbers to give you an idea of the challenges, an additional idea of the challenge. I think you have already an idea of it, and then move to the main part of this lecture. So the protons are run in this ring of 27 kilometers, and because they run at very close to the speed of light, actually speed of light minus 30 kilometers per hour to be precise, they make 11,000 tours of the full ring in 1 second. So it's quite a good pace. In each beam, in the two beams, there are at the same time 10 to the 14 protons circulating. So this means 100,000 billion protons circulating in the two directions, in the two opposite directions. The size of the beams at the collision point is very small. They are squeezed in order to increase the probability that they interact. And their transverse size is 20 micron, which is smaller than a human hair. The most crucial component of the accelerator, which has allowed us to reach such a high energy, is a set of 1,200 superconducting magnets. Being superconducting, they have to work at low temperature, and they work actually very close to the absolute zero. They work at 1.9 Kelvin, which corresponds to minus 271 degrees centigrade, which is actually makes the LHC the coldest place of the universe, because the universe is at 3 Kelvin, whereas we are working at 2 Kelvin. So as we see, it's a very cool project. Also very large is the energy stored in these beams, because these beams are made of many particles which travel at very high speed. And so the energy stored in the beams, when the LHC will run at full power, we are not yet there, will be 350 megajoules. So if you want to have an idea of what this means, this is like a British aircraft carrier traveling at 12 knots. Now, why it has to be British, I don't know, but this is what I found. So I reported, to be precise, I report what I found about this area. The CMS experiments has more iron than the Eiffel Tower, the Tour Eiffel, and weighs more than the Tour Eiffel. In ATLAS, we use 3,000 kilometers of cables to bring the signals from the detector, from the cavern, to the control rooms where the data are recorded. And each LHC experiment produces every year order of 10 petabyte of data. Now today, everybody knows what a petabyte is, but if you wanted to write this data on DVDs, you will need 20 million of them, or a stack of 20 kilometer high. So clearly, the question is why? And the reason is the following, that the elementary particles and their interactions are very well known today. Thanks to a huge amount of experimental work over the last 40 years made at CERN and many other laboratories all over the world, in particular in the US at SLAC, Stanford, so very close to here, Fermilab in close to Chicago, etc. We also have a theory which is called Standard Model, which describes the elementary particles and their interactions, which is extremely successful because it has been extremely predictive. All the particles predicted by the theory have been discovered, observed experimentally, the last one actually in July last year. And the theory itself, the prediction of the theory concerning how this particle behaves, how they decay, how they interact, has been verified by the experiments with very high precision. So it's an extremely successful theory. So clearly, the Standard Model and there are some of the scientists who have contributed to the development of this theory are in the audience tonight, is a correct theory. The problem with the Standard Model is that although correct, because it describes our reality and describes the elementary particle, is that it's not a complete theory. It's not complete because there are several questions that have been raised by experiments, by observation, to which the Standard Model is not able to answer. One question that we are now ticking off is what is the origin of the particle masses. There was some mechanism in the Standard Model which we have now verified, and so this is related to the Higgs boson, and I will come back to this later on. But there are some other questions to which today we don't have an answer. One of them, perhaps one of the most fascinating questions, is what is the nature of the universe dark matter? I mentioned before that only 5% of the energy matter content of the universe is made of ordinary matter, so electrons and quarks, like all of us. The rest is made of a form of energy and matter that we don't know. In particular, about 20–25% of the universe is made of a form of matter, which is called dark matter, because it doesn't interact with our instruments. And none of the particles of the Standard Model, none of the particles observed so far has the good feature to explain the features of dark matter. So dark matter is made of a new particle. So it's made of a particle which belongs to a new theory which is more complete beyond and goes beyond the Standard Model. We don't know why there is so little antimatter in the universe, or if you want, why the symmetry between the matter and antimatter proportion in the universe is so large. We don't understand it. The Standard Model explains only part of it. We don't know if there are additional forces in addition to the four that we know, additional dimension, etc. So DLHC has been conceived and built to address this another fundamental question that I could not list all of them, and in particular to look for physics beyond the Standard Model, because we know that the Standard Model cannot really explain all of it, so there must be physics beyond the Standard Model. And actually, one of the most compelling and best motivated scenarios for physics beyond the Standard Model is supersymmetry, which was introduced by Julius West and Bruno Zumino in 1973. It's a theory which predicts that for each elementary particle that we know, there exists a supersymmetric partner which has very similar, which has features which are identical to the particles in our known world, except one, which I will not explain because it's a bit complicated. This theory is extremely nice. It's not only beautiful as a theory, but also it's very convenient and economical because it allows to answer, to address, and to give at least theoretically satisfactory answers to many of the questions that I've listed before. In particular, among the spectrum of particles predicted by supersymmetry, there is one called lightest neutralino, which are all the good features to explain dark matter. But supersymmetry can also address many others of the questions that I mentioned before, and etc. Now, the problem is that there is no experimental evidence for supersymmetry as yet. Okay, so we have not observed any supersymmetric particle. So there could be various explanations to this. First, SUSY particles are quite massive. We didn't observe them yet because the LHC is not yet running at the full energy, but we hope that by going to higher energy in a couple of years from now, they may become accessible. So they are there, but they are too heavy to be produced so far. Second possibility, supersymmetry exists, but it exists at an energy scale which is very high and which will never be accessible at accelerators. So then we can't really prove experimentally that it exists. And third, the theory is wrong. Supersymmetry doesn't exist. It's a pity, though, because it's a very beautiful theory, and as a UK physicist, Paul Dirac, said, the beauty of an equation is more important than its correctness, in the sense that if an equation is beautiful, sooner or later, it will be demonstrated to be correct. So we do really hope that, given that supersymmetry is so beautiful, such a cute ideas, that indeed this will happen. So I now go to the experimental part and to the discovery of the Higgs boson. This adventure, the LHC adventure, started at the end of March 2010 when first circulating beams in the LHC provided collisions at the energy frontier, at the new energy that at the time was 3 times larger than at the, more or less 3 times larger than at the previous machine. Since then, we have made a lot of progress. So the 3 fundamental components I mentioned before, the accelerator, the detectors, and the computing, have been performed very well beyond expectations, and also the physicists, I must say, have been performing very well. We have recorded a huge amount of data, and with this data, we have made so far 3 things. We have rediscovered the standard model in a new energy regime. That is, we have observed again all the particles that we knew already from previous experiments, from previous accelerator, and we have measured them in a new energy regime. So we have demonstrated that the standard model works at high energy. And we have also looked for many physics scenarios beyond the standard model, supersymmetry, and many other. For the moment, we didn't find anything beyond, so we have, of course, ruled out some possibility and constrained several models. But most importantly, last year, we have reported the discovery of a new particle, which at the time we called Higgs-like, because we were not really sure it was the Higgs boson, but I will show you today that we are a bit much more confident. And this particle has a mass typically of 130 times the mass of a proton. So this discovery is very important. Why? Because it allows us to understand what is the origin of the particle masses. That is, why the photon, which we all know as constituent of light, of the light, is massless, is just pure energy. And the photon is the particle which, in quantum mechanics, at the microscopic level, is responsible for transmitting the electromagnetic interaction between, for instance, 2 electrons. So why is the photon massless? Whereas the W and Z particles, which are responsible for transmitting the weak interaction, which is responsible, for instance, for radioactive decay or thermonuclear interactions in the sun, why the W and Z particles have a mass typically 100 times the mass of the proton. Why the heaviest elementary particle observed so far, this is the top quark, which was discovered at the Tevatron Collider in 1995, has a mass comparable to that of a gold atom, whereas the electrons has a mass which is 350,000 times smaller. The concept of mass in physics is a bit delicate, so here I'm really mixing gravitational mass with inertial mass, but anyway, I don't want to go into this detail. So why is it like that? In the 60s, at the beginning of the 60s, a group of theorists, among which a Scottish theorist, Peter Higgs, but few others, 5 more, introduced a mechanism which was called Higgs mechanism, which explains how particles get a mass. So I will try to explain to you how this happens in a very simple way. So my colleagues, physicists in the room, are kindly requested not to listen, to fall asleep for the next 93 seconds. The time will take me to explain, and so I will try to explain you what happened. So imagine the universe just after the Big Bang. Immediately after the Big Bang, it was very hot, and all particles were massless. They were just energy, and so they were going around in the universe at the speed of light. And imagine that the universe was permeated by a medium, but this medium, we call it a field in physics, but this medium was transparent, like ether, vapor. The particles could not see it. So they were going around happily at the speed of light and without mass and just pure energy. And then the universe, the temperature goes down. After the explosion, the temperature goes down. And at some point, and this happened 10 to the minus 11 seconds, we think it happened 10 to the minus 11 seconds after the Big Bang, so 100 of a billion of a second after the Big Bang, this field becomes more solid, more consistent. So what happened actually is what we call in physics a phase transition, which is a complicated term for describing, for instance, when water becomes ice. Temperature goes down, the water goes from a liquid state to a solid state. Similar thing here. There was some ether, some transparent medium, and this medium at some point, the temperature goes down and becomes something more consistent. Imagine some kind of jelly thing, some kind of molasses or jam, marmalade, something like that, okay? So now the particles, actually some of them, realize that there is something in the universe. It's not really empty space or transparent medium. And imagine that these particles are like little balls. If the surface of the ball is perfectly smooth, and this is the photon, the particle continues to traverse the medium without noticing it. And this is the photon, which continues massless at the speed of light. If the surface is more rough, then a particle starts to stick the marmalade, the jam, and becomes massive, and it is more and more massive, and it is slowed down. So this is the mechanism by which particles have acquired a mass, and some particles acquired a mass, some did not. Now, I will tell you also in the more rigorous way, so that my physicist colleagues see that I know something. So actually, the mass is acquired through interaction of the particle with the Higgs field, which has a vacuum expectation value which is different from 0. This is the more rigorous formulation, so that I see that at least I know a bit of physics. Anyway, so this is a marvelous mechanism. The problem is that this mechanism predicted as a consequence of the Higgs mechanism the existence of a new particle called the Higgs boson. And the little problem was that this Higgs boson had been searched for more than 30 years at accelerators all over the world, and was not found until July last year, where we finally found it. Okay, so I'm sure at this point you would like to ask a very legitimate question, and the question is, what's the question? The question is, who cares? Who cares about the particle masses, all these things, the molasses, the field? So actually we should care, because if the Higgs boson, if the Higgs mechanism was not there, we will not be here. The atoms could not stick together, the universe would not exist, or would be very different. We are what we are because the elementary particles have exactly the masses they have. A tiny difference in the mass of the quarks, for instance, could make the proton decay. If the proton decays, there are no atoms, there is no chemistry, there is no universe, there is no nothing. Or there could be a universe, but completely different. So we are what we are because the elementary particles have exactly the masses they have. Except that until July last year, we didn't know how this is possible. We didn't know if this mechanism was correct. Now we know that it's correct. So, how did we observe the Higgs boson? Well, the Higgs boson, once produced, decays immediately, disintegrates in known particles. For instance, it can decay into 2 photons, and the photons are very well known in our day-by-day life. So we look at the events recorded by ATLAS and CMS, and we look for events that contains 2 photons, and then we look at their spectrum, and typically the spectrum is something which falls like that, and if you have the production of a new particle, then you see a bump. And this is the Higgs boson. This is one event recorded by the CMS detector. You see that 2 yellow arrows indicate the direction of the 2 beams. The beam collide here. In the middle of the detector, you see many tracks coming out, and you see these 2 green lines indicate the energy deposited by the 2 photons in the detector. So this is how a Higgs event would look. We have also observed a Higgs boson decay into 4 electrons. I have taken this example also because electrons are also very common in our day-by-day life. So this is an event recorded by the ATLAS experiment. You see the collision point here, and these lines indicate the energy measured by the detector. It was not easy, because one such event is produced every 10,000 billion proton-proton collision. So it requires a very meticulous and very serious experimental work to extract such a tiny signal from the bulk of collision, proton-proton collision, which give rise to processes that were already known. So I will now anticipate three questions that you may want to ask. And the first one is the following. Is this new particle the standard model Higgs boson? And the answer is that the present measurement, the present data, say that it's very much like the standard model Higgs. However, of course, we cannot draw definite conclusion yet, so we will need to measure its properties in more details in the months and years to come, using the data we have already recorded and more data that we will record at higher energy in a couple of years from now. It could be the standard model Higgs boson. It could be another object which has a similar task, belonging to a more complete, a more general theory. Of course, we would prefer the latter hypothesis because this will be a clear indication of new physics. But for the moment, we cannot tell. It looks very much the standard model Higgs boson. The second question is the task of DLHC over? And the answer is no. We are just at the beginning, not only because now we have to measure in all details these new particles, but also because, you remember, I showed you a long list of questions of which the origin of the particle masses, so the Higgs boson was just the first one. So we are ticking off the first one, but all the rest is there. So we will continue to look for dark matter, to try to explain the matter-antimatter asymmetry in the universe, and many other things in parallel. So we are just at the beginning, and we have to address many other questions. And the last question is, will the Higgs boson change our day-by-day life? And in my opinion, the answer to this question is it did already. And the reason is the following, is that because to be able to discover the Higgs boson, we had to develop so much technology, so many technologies in many fields, cutting-edge technology, that we have already transferred to society, that the Higgs boson, in some sense, had already an impact on society. I mentioned at the beginning the World Wide Web, but this is not the only example. We have today in the world something like 30,000 accelerators, and more than half of them, 17,000, are used for medical application. For instance, cancer treatment with hadron therapy, and they've been built using technologies developed at CERN, at Fermilab, at SLAC, and in other laboratories in the field of high-energy physics and nuclear physics. Likewise, in medical imaging today, many scanners are used, and one of them, or several of them, are based on the instrumentation that we have developed for our detectors at CERN. So, to find the Higgs boson, we really had to made a lot of progress in many fields, and this progress already had an impact on society. So I'm concluding. At CERN and with the LHC, we are looking for answers to a fundamental question about the elementary particles and their interaction. And in order to achieve this goal, we had to push forward the limit of technology, that of course this goes also to the benefit of society. One of our goals is also to train the young generation. You have seen in this experiment we have thousands of young people, so for them it's very important also to participate in international projects like ATLAS and CMS, where they are exposed to peers from all over the world. So it's a very good way of growing and interacting with people from all over the world. So it's also a fantastic way of bringing nations together. And with the advent of the LHC, a new era of discoveries has started, which has already been awarded by a very special, very important discovery, the observation of a Higgs boson, which represents a big step forward in fundamental knowledge. I have tried to stress the social benefits of what we are doing in terms of collaborating with people from all over the world, concrete example of peace, spin-off in technology, etc. However, I would like to stress that fundamental science and fundamental research justified by itself, because fundamental knowledge is the fuel of progress and of any applications. If you have no ideas, no innovation, no new step forward in knowledge, at some point progress becomes sterile, it stagnates. And second, knowledge as art is among the highest expressions of human beings as clever beings, which they distinguish us from animals, and therefore they need to be pursued and encouraged. An Italian poet of the 13th century, Dante Alighieri, wrote something like, he wrote "Fatti non foste a vivere come bruti, ma per seguir virtute et conoscenza," which means you were not born to, you were not created to live as brute, as animal, but to pursue virtue and knowledge. So not supporting, say, for instance, cutting funding to art because it doesn't have an immediate impact on our day-by-day life, for me, is one of the most stupid things that we could do. So art and knowledge really should be supported, because otherwise we are going to alter the nature of mankind. Thank you.
Thank you, Fabiola, for this really wonderful and awe-inspiring lecture. We have some time for questions. And before that, can I say something? There are many distinguished physicists in this audience. They will answer the difficult questions. They are already there. I have already located a couple of them. They know because I already pre-warned them.
Oh, all the way in the back.
Wonderful lecture. I was wondering if you considered nanosizing your project, because it's awful big, and working on new techniques with microscopy to see even smaller levels. If you nanosized it, I'm sure you'd have to see much smaller than the micrometer. Thank you.
Yeah, I would be happy to reply if I had heard the question, but I have an echo here. What did you ask exactly? Can someone repeat the question? I didn't hear at all. Can you come closer, because I come here. Very good. Tell me. Hi.
Hi.
Nice to meet you.
Nice to meet you. Nanosizing, using nanotechnology to recreate your experiment on a smaller level, and then using microscopy to look further than the micrometer, beyond the nanometer.
Well, we are...
That's the question. Thank you.
It's a question or it's a statement? Because there was a question mark at the end. Okay. So, it's a question. So, well, nanotechnologies, of course, are used in the, will be used more and more also in our instruments as soon as they become available on large scale. Because the problem with these experiments, of course, is that we need, they're big. So you can't just have one little chip. You need millions or billions of chips like that. So this will be used. Now, the problem is to create the condition, the energy condition, to be able to go down scrutinize matter at a very small scale. So this is the problem. To be able to, with the energy that you produce in your accelerator, to observe matter on a very small scale. So I don't know if it answered your question, but your question was not really addressing the problem, was more addressing the instrumentation part of the problem, not really how to be able to create the energy condition which allow us to study the fundamental constituent of matter.
We have our next question here.
Ah, very nice.
I'm really sorry to say that I lost track about halfway through this lecture, but so from what I understand, even though an electron does not have any actual matter, it's that small, it still has an actual weight, right?
Sorry?
Just because an electron is so tiny, it still has an actual weight, right?
Yes, the electron is a very small particle that cannot be cut into smaller pieces, okay?
So have scientists actually figured out how much an electron would weigh?
Ah, would weigh. Ah, okay, sorry. So here you are, the problem is that the concept of mass is a very difficult concept. It's not, there is not one concept, only one concept of mass. The mass can be interpreted as gravitational mass when we When we weight you on a balance, okay, you have a mass in your body, okay, which is not given by the Higgs boson, unfortunately, and I don't want to disappoint you, but the Higgs boson only gives mass to the elementary particle, and most of our mass comes from other sources. And then there is what we call the inertial mass. And the real definition of mass is, in some sense, the, opposition, the resistance that a particle produces to a force. Okay, so I want to accelerate you, but you have some mass. I'm not able to accelerate you. Okay, but we are not going really to weight. We can't weight the electron, unfortunately. So we have to deduce its mass from from experiments which measure the electron properties.
Thank you.
You said earlier that the photon is smooth, and the other. I'm sorry.
I use this kind of image, but it's not scientifically.
Okay. And the other particles have roughness, and that's part of how they interact with the Higgs field. Is the roughness fractal?
So I should use another example next time, because
okay.
I didn't want to bring to.
I'm sorry to get you in trouble.
No. What I wanted to say simply to explain. Well, okay, fine. So no, the question is, the problem is that the Higgs field, it produces it's an interaction of the particle with the Higgs fields which give them mass.
Yes.
Okay. So. The mass is only given to the W and the Z boson, which are the carrier of the weak force, but not to the photon, which is the carrier of the electromagnetic. So what I wanted to tell you is, like if you have particles going through a medium, and one of them does not really see the medium, and this is a photon, and the others, on the other hand, see the presence of this medium, interact with it, and they get a mass which is proportional to the strength of interaction.
Okay, thank you.
Next time I will use another image.
I'm trying to get a basic idea here. Between the standard model and supersymmetry, is the prediction of the Higgs boson different? Is that the right way to phrase it?
It's a very good question. Yeah, supersymmetric theories actually predict the existence of more than one Higgs boson, so actually 5 Higgs boson. And this will be very nice, because of course we will find. But in the most motivated models, the lightest Higgs boson has features which are very similar to a standard model Higgs boson. So today we don't know if what we observe is the standard model Higgs boson or the lightest Higgs boson of a supersymmetric theory. So by measuring its properties, we can try to understand if it is really the standard model or a Higgs boson belonging to a more general theory. But of course, the most obvious step would be if nature was so kind to make us observe, to allow us to observe the other Higgs boson and the full spectrum of supersymmetric particles.
Here we go.
I'm trying to understand, was the interaction with the Higgs field, was that a one-time thing? And
No,
that they got their masses then, or
is it
continuing forever?
The vacuum is not empty in physics, so the Higgs field is there. No, it's not a one time, it's always there.
I was just wondering, so when you are colliding the two beams, right, and they're very thin, so how do you make sure that they will not miss each other but hit right onto
The two beams?
Yeah.
The two beams are controlled through a series of magnets, different magnets, dipoles, sextuple, octupoles, which are able to control their orbit at the level of the few micrometers. So they are extremely well controlled, and the accelerator has been built with specifications such that the beams can collide with that kind of precision. So they are extremely well controlled. Also because these beams, as I said, have a lot of energy. This famous British carrier traveling at 12 knots, okay? So if one of these British aircraft carrier goes out of the orbit, you can imagine that it's not really nice for the magnets that are around the beam pipe. So the beams need to be controlled with very high precision, and they are indeed by using a set of magnets and very complex optics that allow that allow, to allow us to steer them with very high precision.
Are they pulsed beams?
Are they?
Are they pulsed? Are they concentrated? Are they?
No, and yes. So they're not pulsed; they're continuous beams. However, it's not a beam. Is not a flow of a continuous flow of particles. The particles are grouped in bunches, separated by 50 nanoseconds. Okay, so they're not pulsed in the sense that you inject, that you have. They are concentrated, exactly. They are concentrated, so they circulate all the time, but they are concentrated in bunches which are separated by 50 nanoseconds, and every bunch contains 100 billion protons.
We've got.
I don't know if I misheard you, but I thought you said more studies need to be done. So does that mean that the Higgs boson particle the scientists are not 100% sure it is the Higgs boson particle?
Okay, so there are two types of questions. One is if this particle behaves like a Higgs boson, that is a particle which is able to give mass to the other particles, okay? So there are a certain number of fingerprints which allow us to understand if this particle is of the type of Higgs boson, okay? And we've started to measure these fingerprints, and it seems that really this particle is a Higgs boson. So it's a particle which interacts with the other particles in a way proportional to their mass, and it has also some intrinsic feature which is called spin, but I don't want to go into details, which is in agreement with what we expect for a Higgs boson. So it is a Higgs boson. Now, what we don't know today yet, if it is the standard model Higgs boson, or perhaps it is a Higgs boson of a more general supersymmetric theory. So there are other Higgs bosons. Okay, this we don't know. But we think we can say today that it is a particle of the class of the Higgs bosons. There are questions.
Do you want the mic?
First off, that was a great lecture. Thank you.
Thank you.
I don't understand something about these experiments. Your particles are traveling very close to the speed of light, and then we speak of the mass of the particles. Are we speaking of the mass of the particles at the speed of light or near the speed of light, or are we speaking of some form of rest mass?
No, we are talking about rest mass when we speak about the mass of the particle, yes. But from the point of view of the experiment, this is irrelevant. I mean, from the point of view of the detection of the particle is quite irrelevant for the detection technique. So it's...
Thank you.
Well, I've seen several hands there.
Hi, it was a great lecture, by the way. I want to thank you.
you.
I don't quite understand something. If you could correct my understanding, this would be great. I take to understand that the leptons, quarks are all within neutrons, protons, and those are the basic elements below protons and neutrons. But how does an up quark, for example, have more mass than a gold atom if it is consisting of quarks and leptons?
Top quarks is not part of the nucleus. Okay, so the neutrons and protons are made of light quarks, up and down quarks. Only two types of quarks. Not all. Yeah, I should have said it. So it's not. Okay, when I say that we are made of quarks and electrons, we are not made of all possible quarks. Okay, so the main components of the neutrons and the protons are two types of quarks, up quarks and down quarks, which are the lightest one. There are also some others, but in a completely negligible proportion. I don't know if this addresses your question, but this is the...
Last year, they believe they didn't know whether it was a spin 0 or spin 2 particle. Has there been any resolution on that?
So I didn't want to go into many details, but one of the fingerprints of a Higgs boson is that this particle has a quantum number, so it's a feature, intrinsic feature of that any particle has, which is called spin. The spin is associated with a kind of rotational motion of the particle, a kind of intrinsic angular momentum. All the particles discovered until the 4th of July last year well, we had discovered 16 particles, belong to two fundamental classes. What we call matter particles, called like that because the quarks and the electrons belong to these particles, which have a value of this quantum number called spin, which is 1/2. And then the other class was the class of what we call the force carrier, so the particles that are responsible for transmitting the fundamental forces, like the photon, the W, and the Z boson, which have spin 1. The peculiarity of the Higgs boson is that A is not a matter particle, is not a constituent of matter, and is not a particle responsible for transmitting force. It's a particle which has a completely different task, giving mass. And second, it has spin 0, is a scalar. And this is very important also for some cosmological implication. So the data of the two experiments, ATLAS and CMS, clearly favor in a strong way the spin 0 hypothesis against other spin hypotheses like spin 2. So that's why I replied before that we think this particle is a Higgs boson because it has the two fundamental features of coupling to particles in a way proportional to their masses and the spin 0.
Hi, thank you, Fabiola, for a wonderful lecture. I have just one question. On the Higgs boson that you've been mentioning, you told me who Higgs was, but who is boson? And how did that, I know there was a Bose there.
It's a very good question, and I think you know the answer. I think from your accent, I understand that you know the answer. So, of course, you are alluding to Bose, an Indian physicist, and it's called bosons, like the particles which have a spin 1/2 are called fermions, so Fermi, sorry, I'm Italian, so I have to because particles with different spins obey different kind of statistics, as we say in technical terms. That is, you can put many bosons all in the same energy level, in the same state to state, whereas you cannot put more than one fermion, say. So it's called boson because it has a spin, essentially spin 0. Okay, so I think we should really tribute Bose, of course, because it's...
This is the last question.
Okay.
Yes, I had a quick question. Is the Higgs boson and the Higgs field subject to the effects of entropy? And could you give like a really fast explanation as to why or why not it would be affected by entropy?
I think I didn't understand anything of what you said. Can you repeat? Are you mentioning what I don't know if you were talking about the dark energy you mentioned, cosmology?
Entropy.
Entropy. Yes. Here I need Nima or Hitoshi. Did you understand? Or Pierre. Entropy. Yes, entropy. Yeah, I understood entropy, but I don't understand the question. I didn't understand the question. Can any of my friend physicists help? John, did you understand the question? It's yes.
So entropy is a very general feature of physics, and the Higgs field, the Higgs boson, they participate in the law of entropy the same way that electrons or photons do.
Thank you.
This was an answer from John Ellis from CERN. So I think on this note, let's thank Fabiola again for a wonderful lecture.